Hello everyone, Mr. Tomaszek here. Today I want to talk to you about a topic called specific heat. Now what is specific heat? We'll elaborate in a minute, but that's a characteristic property of substances such as copper or brass or aluminum. Any substance, even water itself, has a specific heat. Before we jump into that though, let's do a quick review of what we talked about last time. What is heat energy?
Now, last time we defined heat energy as the energy contained in a substance due to the kinetic energy of its molecules or the atoms. All right, a good example is like a sample of water, where you have water molecules that are always in constant motion and they bounce off the sides, the bottom, each other. They might spin and twirl, they might stretch, and so on. All of that movement is kinetic energy, and some of them are fast and some of them are slow. If we heat up this substance, they start to move faster, and the average kinetic energy goes up. Let's watch Bill.
The hills are alive with the motion of molecules. Ha! See, even cold things have heat. Things like snow and icy mountain lakes and glaciers. They've got heat. Anything with molecules has heat. It's just that the molecules in cold things are moving more slowly than the molecules in warm things. You with me?
Now, temperature is a measure of that average kinetic energy. If the molecules get colder, they start to move slower and the temperature goes down. And if the molecules move faster, the temperature goes up. So temperature is related to heat energy, but is not exactly the same thing. That then brings us to this topic called specific heat. Specific heat is the heat needed to raise the temperature of 1 gram of a substance by 1 degree. This is the main equation for this unit. What does it tell us? First off, Q equals M times Cp times delta T. Q is the symbol that we use to represent heat. Heat is energy, measured in joules or possibly calories. M is the mass of the substance. Here's a list of substances. And Cp, or sometimes just C, is the specific heat capacity. And that's a characteristic property of the substance that you're talking about. For example, water, glass, aluminum, they all have their own specific heat. The third term is delta T, that's the change in temperature. So if you wanted to warm up or cool down a substance, how much heat energy it would take in joules would depend on the mass, the characteristic property called specific heat capacity, and how much you want the temperature to change. So the more you want the temperature to change, the more heat energy it's going to take. The more mass you have, the more heat energy it's going to take. All right. Now it works both ways. You could add heat to it and make the temperature go up. You could take heat out of it and make the temperature go down on there. All right. Notice on this chart then a few examples of specific heats. Water now being has a very high specific heat relative to things like glass, aluminum, copper, or mercury, which means that it takes more energy to warm up water than it does most other substances. That being said, once the water is warmed up, it holds a lot of heat energy in it as well.
This is what makes living on the earth possible, because the oceans hold huge amounts of water and also a huge amount of energy. So it sort of helps maintain the temperature of the earth in a very narrow range, so it doesn't get too hot, doesn't get too cold. Sometimes the sun warms up the oceans, and then at night they cool down, and it maintains pretty close to the same temperature on a daily basis.
Now,
every substance has its own characteristic specific heat, whether we're talking about water or glass, the container that it's in, or maybe aluminum or copper, which we use for making pipes for your water in your house, or mercury. Now, I don't have any mercury, except I do have a little bit in what's called a mercury switch. Let's take a look at that. All right, mercury is an interesting substance because it's a metal that conducts electricity, and it's a liquid at room temperature. Now, we can't have this in schools anymore because of the toxicity of it, but in the old days, we used to use them in the switch. This particular switch right here is called a mercury switch, and notice that when we tilt it, it can turn that light on and off. This one used to be inside of a pinball machine, if you've ever seen a pinball machine. Those little things that got little paddles on the side, and you flick the ball up the hill. If you were to tilt the machine, it would sense that you tilted it, and then it would shut off and you'd lose your game there. That's mercury. Anyway, I show you it because it is on our list. All right, let's look at an example. Let's say we want to heat up 325 grams or 325 milliliters of water. How much heat energy would that take? All right, so we would need to have a heat source, perhaps a candle. And we're going to do a lab with this apparatus here in a little bit. So here's our question. How much heat would be absorbed by 325 grams, which in the case of water is equal to 325 milliliters, when its temperature is raised by 35 degrees. So depending upon what temperature it starts at and what it ends at, its temperature change is 35 degrees.
So to calculate then, we'll take the mass times the specific heat, which is usually something that's given, times the change in temperature. Maybe it goes from 25 up to 55 degrees, and the change in temperature is 35 degrees. Then we could calculate how many joules of energy it would take. Now, joules usually ends up being a large number because joules are a very small amount of energy there. So that's a very typical example. If you want to heat up or cool down, if you want to take the heat out, you can do that too as well. So this equation is the equation we use when we want to warm up something or cool down something or just generally change the temperature of something. We have to know three things. How much of the stuff do we have in grams, the specific heat, which is on a per gram basis, and the change in temperature, which could be either in Celsius or Kelvin, because we're talking about a change in temperature, not rather an absolute temperature. Okay, let's finish with a little bit of vocabulary. We have these terms we call endo and exothermic, and all kinds of processes are either endo or exothermic. Now, endo means heat goes in. Exo means heat comes out, kind of like to the exterior or the interior, like that. Now, we could apply this concept to processes of change of state. For example, if I want to go from a liquid to a gas, we call that evaporation. All right, evaporation. And that would require the input of energy to vaporize a liquid to a gas. We could go from a solid to a gas. We call that sublimation. And we could go vice versa too. We could go from solid to a liquid. That's what we call melting. Now, any one of these is a endothermic process. So the ones that are in blue are kind of purple here are endothermic processes. If we go from a gas to a liquid, we have to take heat out, and that's an exothermic process. So taking heat out would be condensation or freezing, or going from a gas straight down to a solid is what we call deposition. All right, chemical reactions can be exo or endothermic. Other processes like dissolving solids into water or one kind of liquid into another could be endo or exothermic. So we'll use this terminology applied to a lot of different things. And we just looked at how we can measure the heat, Q, for changing the temperature of a substance, mc delta T. We will also look at the heat, Q, needed to melt a substance or freeze a substance or evaporate a substance too as well. That will come a little bit further down the road. All right. A couple more terms. Calorimetry, which is what we're going to do in a lab here in a minute, is just sort of a way to measure heat changes during chemical processes, whether it's a phase change or a chemical reaction or something on that line. Enthalpy is a fancy word for heat content. All right, if you have a beaker of water, there's molecules in there, and they're all at a certain temperature, and there's an average kinetic energy, and there's a heat content in that. Now, each substance, when you form it, for example, H2O formed out of hydrogen and oxygen, there's a certain amount of heat content that's in each one of those molecules, and enthalpy kind of relates to that. All right, we use the symbol H for enthalpy, and it applies to a lot of different things. Some of the things that we might not even really get into with this. All right, so that's kind of a quick synopsis of what specific heat is. And we have that equation Q equals mc delta T. And we'll use that for many, many different calculations and experiments.